So our next speaker is Dejan Markovic from UCLA. He'll be telling us about closed-loop neuromodulation.
All right, thank you, Gert. Good morning, everyone. I will talk about advances of closed-loop neurotechnology. I'll show a lot of technology, but keep in mind that everything starts and ends in clinic. So technology really has only that purpose in all that I'm going to describe today. There is accumulating clinical evidence that points to the effectiveness of closed-loop neuromodulation with existing devices. There are two DBS studies with a small-scale patient size to show that you can achieve equivalent outcomes with applying stimulation only 45% of the time as opposed to continuous stimulation. And also a UCSF study that shows that you can, again, achieve similar outcomes with 40% less energy, which is good to minimize side effects, prolong battery life, and all the benefits. There is a paper by Dr. Lozano that talks about the needs for closed-loop neuromodulation in Alzheimer's patients, and a recent paper from last year from UPenn for the memory indication. So all of this is really kind of pointing to the technology gaps that we need to address as a community, which includes higher specificity, meaning higher number of channels from which you need to record. You need to record full duplex simultaneous with stimulation, with real-time wireless telemetry and power charging, and miniaturization to support higher channel count. And all of that is attainable considering the state of the current clinical technology, which is few decades out of date. To transition into technology and how we address this, I would like to honor the legacy of UCLA in brain-computer interfaces. You may or may not know that BCI originated at UCLA in 1973 in Professor Jacques Vidal's lab, who introduced the term brain-computer interface, and in 1976 showed the first experiment with volitional control of the 2D navigation task, which is really the foundation of BCI. And from the 1973 paper, you can see here the infrastructure that he envisioned at the time for BCI research. You see the control, the experiment room where the animal or the subject, human subject, is interfacing with joystick for navigation that is showing the outcome on the display. Then you have the control area, which is operated by a scientist. And then finally, you have the closed-loop algorithms in the computer area. And at that time, this had to be such a large distributed system which connected to the campus computer, which had only 4 megabytes of memory. And you can see that this computer was actually connected to ARPANET, which was another big invention from UCLA, the internet. We just had a 50th anniversary of internet earlier this year. And then to see how this actually translates to science and to therapeutic, which is where we really want to get. This is the experiment from Duke University and MIT showing that you can transfer brain signals through the internet to control robotic arm. And I just want to plug in here that this is the use of two UCLA technologies, the internet and the BCI, to accomplish this. Later on, the same group demonstrated two monkeys, Aurora and Ivy, playing video games in a 2D navigation task to the point they realized, I don't need this joystick anymore. I can just control this with my mind. And that's exactly the type of BCI people want to translate into humans, which is done at Stanford University and many others in 2017, showing typing on a keyboard on a computer screen for a quadriplegic. The technology behind all of this looks like the NeuroGate, the BrainGate technology that you can see here. You have a Utah electrode array, an external device that decodes this signal and sends it to a computer to figure out the intent and substitute the functionality of a limb that needs to be restored. Fast forwarding to this year, this is the Neuralink, which was mentioned in the previous presentations, the very impressive robot for the insertion of the needles into the motor cortex, very high density, high channel count technology for BCI type application, which is in current development. However, these are great tools for science use, and the clinical translation is a whole another step. In fact, I would like to bring your attention to the epilepsy monitoring, which is the only really kind of golden opportunity to observe deep brain structures with a large number of channels, which is the well-justified clinical opportunity to do translational science for pretty much all of the disorders in human patients. And this is a typical montage of a patient at UCLA, courtesy of my colleagues from neurology, Dr. Rick Staba and Dr. Fried, that are implanted with deep intracranial arrays. These are the patients pharmacologically resistant to medication. And then they take the opportunity to look into areas that are of interest to science. So we can actually use the epilepsy monitoring as a justification to study things like human memory. And this is the electrode array that's being used over 2,000 times, that was designed again by UCLA clinical team, Banke-Fried electrode array. And here you can then study translation to, for example, human memory. And so this is the some of the interesting science that came from decades of research at UCLA to show that unlike motor cortex and BCI that people do, human memory is non-topographic, meaning that two adjacent neurons can encode entirely different concepts, and there is the need for higher specificity and the ability to even record at single neuron level. And so this is the video here that shows the activity and the firing of a neuron in gray matter in the medial temporal lobe from the memory area, and the response to various stages. You can see here, patient is looking at various interactions of people and various environments, and the neuron is quiet completely, despite all the kind of, diversity in this scenery and people that show up to the point that Jerry Seinfeld shows up. And this neuron really just only likes to respond to Jerry Seinfeld. It was also later found that the neuron responds to other characters from the Seinfeld TV series, which gave rise to the theory of associative learning that was researched for decades and then again goes completely silent. So you need a higher specificity to really encode specific memories and cognition. So going further into the clinical therapeutic world, DBS for Parkinson's disease is pretty much the bread and butter of the technology that is used for treatment of movement disorders. And it is now a routine surgery. It's been performed a couple hundred times already at UCLA and other major clinical centers. And this is the technology that is still made from the cardiac pacemakers from a few decades ago, and it's adapted to DBS. And you can see the time scales here from the concept of the idea in the 1950s to the FDA approval, and it's been around for more than 15 years. I will share with you how this looks like in a clinic, just to really understand what are the technology environment in which this needs to happen. So this happened to be surgery number 500 at UCLA a couple of years ago, and my colleague, Dr. Nader Pouratian, had the honor to do the milestone surgery operating on a famous musician, Brad Carter, to
It's not brain surgery. Actually, it is brain surgery. A team of UCLA doctors implanting a pacemaker in Brad Carter's brain to treat hand tremors. But check this out. During the operation, the actor and musician was awake and he was playing the guitar. Strumming the chords actually helped guide the surgeons as they placed an electrode in his brain.
My music's really important to me, so I'm hoping that this will allow me to do that, to play guitar. I'm a finger picker. I want to record. I want to perform live again.
It's the 500th time the UCLA surgical team has performed this procedure. It's the first time that they tweeted it and had a live stream.
That is so cool.
Isn't it?
And so if you look into where we are today, we are quickly headed to neurological disaster unless we do something different. Because dealing with Alzheimer's, chronic pain, depression are some of the largest unmet needs in medicine today. The annual spending on managing these indications in the United States alone exceeds $1 trillion per year. And there are many patients who have tried one medication after another for years with no relief and are at a point when clinicians have nothing left to offer. And believe it or not, one of the most promising approaches for this is to use deep brain stimulation devices, or DBS. But these outdated devices that are focusing on single targets are just not able to automatically adjust stimulation dosing without you going to see a doctor every couple of months. And in fact, I was just reading news, in today's news in the UK and Canada, there is a story about DBS, the first one in North America for the treatment of alcoholism. It is actually interesting because the first subject to enroll in this study is Dr. Plummer, who is a famous Canadian scientist and physician who was treating his work stress with excessive amounts of alcohol, and it really got to the point where after continued to do so after his liver transplant, so he came to the point of enrolling himself into a human study of 6 patients that was dealing with the treatment-resistance alcohol use. So there are more cases like that, but you know, accessing these kinds of indications is really afforded in this kind of epilepsy monitoring, which allows you to access functional networks of the human brain. Because you know, you cannot treat new indications with old tools, and people have tried to do that before. You may be aware of the failed depression trial, Broaden trial, which was using the same continent-level access with 4 to 8 contacts with the brain to try to treat depression. And if you look into all of the neurotechnology in the brain, Parkinson's disease and Cochlear implant are the only 2 successful technologies because the tools are at the right scale in those technologies. And even despite that, we have a penetration of only a few percent, 7% of Parkinson's disease patients. It's even less in the Cochlear implant, despite its, you know, numbers that you misled with. And the bottom line here for the treatment of all these other networkopathies, we just do not have the tools that are at the right scale to diagnose, to create translational science, and finally offer therapy. So Cochlear implant is one of the most successful, but you know, it takes a decade for a patient to accept this type of technology because you can see there is this external device which is really creating a social barrier for patients to do that. And if you try to do something similar for mental health, that's going to be super challenging. Another very impressive piece of technology, perhaps the most interesting, is the Retinal implant. But you can see that it's currently being used in only 75 patients per year. That's also reflected in the cost of the device. And technologically, this is really the most difficult piece of technology because of the challenges with detachment of the electrode to the retina, the wireless power transfer, the movement of the eyeball to kind of create this more interesting, and ultimately, you know, the amount of technology that you put versus the outcome that you get. And so we come to the point where there were a lot of these kinds of technologies that were built in the real world, and government invested in a lot of these resources, and then they came to the question, how can we take this to the next step? To make these technologies to be clinically efficient and sustainable. And that's where the President's Brain Initiative came several years ago. And one of those programs was the program called SUBNETS, which was really oriented on understanding of network-based systems, complex disorders that were motivated by mental health issues in military for the government. But the idea here was to create a technology that has many more intervention points, that you go from the continent level access to the country level access with hundreds of contacts, bringing together fundamental and translational neuroscience, neurology, animal research, and human work to build next generation technology that allows us to do this. And now we can do that because we understand brain networks well enough to be able to access and manipulate them. Imagine that you can record from multiple locations in the brain at the same time and self-adjust automatically to optimize therapy and minimize side effects. That would be a really kind of paradigm shift in how we look into treatment of patients. And there was a lot of excitement about some of the early clinical evidence to show that we can actually do that in mental health patients. And so this is coming from the DARPA D60, which is the 60th anniversary of DARPA, showing highlights of the technology that was coming from the SUBNETS program from Dr. Eddie Chang's lab at UCSF. And I'll play you a video of a patient. Again, this is epilepsy monitoring patient who has developed severe anxiety on top of that.
Downhill very quickly, and I get such bad anxiety from nothing all of a sudden.
So that's no stimulation, and now the stimulation is turned on.
Before you said you were calm, are you still feeling calm?
A little more excitement, maybe. There we go. It's good.
Okay.
Look at that.
Do you think that, do you know why you're feeling that difference?
No. I don't actually. My goodness, all of a sudden, I'm like, I have some energy. But I like energy.
Okay. So that feels good?
It really does.
Okay.
Wow, what did you guys do? This is excellent news.
Does this kind of excitement that you're feeling, is it something that you feel on a good day, or is it something that you never feel?
Oh, good days.
Okay.
Oh, yeah, there are so many things I just love. Love to do things when I'm not having. See, this is normal.
And so for a patient with mental health to say this is what normal looks like is absolutely amazing. So we then developed, in response to this, a platform neurotechnology that allows us to sense signals from multiple locations in the brain, aggregate them to a hub to make this modular, send it down to a controller, and in response, controller sends power and therapeutic stimulation that is localized and individualized to each patient. So we see this as a platform technology that has the implant as the centerpiece of this, and it is made to be R&D technology for the demonstration of feasibility. This would need to have higher maturity point to be really mainstream, chronically viable implant, but it was meant to show closed loop operation with up to 256 channels with wireless power and data, and we had external module to program this device. We had also user connectivity to synchronize with the electrophysiology, and the idea is to be able to log all this data into the cloud and have informed follow-up when needed. Just to highlight a few pieces, this was a major undertaking. One of the most interesting parts was the human-grade neuromodulator, which is a 64-channel medical-grade device that does a full duplex sensing and stimulation and fits in a size of a vitamin pill, roughly speaking. We call this as a smart lead neuromodulator. And then the control module, which we built together with collaboration with Boston Scientific, who provided the packaging and guidance on how to do this properly. These are the electrode arrays, which have 64 contacts that are for cortical and subcortical use that are attached to these electronics. So we have only 6 contacts that come on the other end. And just to kind of give you a visual summary of this after 5 years of effort, this is what we did in building qualification units. This is the whole implant device with cortical and subcortical smart leads going into the aggregation module and the chest module, and we've built qualification units, really dozens of these, to be able to verify them at various stages. And a couple of things just to highlight here. We've even built cables and data antennas and dealt with the chains of vendors, and this was really kind of amazing experience. just the amount of documentation that you needed for quality control, design history file on all of this is totally non-academic. I've counted the last time was about 150 files that we needed to really kind of maintain and do the proper documentation, and nobody talks about that. And you know, things that you just have to do because you have to do and don't publish, you just have to do it. But you know, two things, and nevertheless I want to highlight, are that we have passed all of the manufacturing requirements from Boston Scientific for building the electronics into their chest module. And when I say that 37 out of 47 units fully packaged pass, doesn't mean a lot, but you have to really look into a 50-page report and 22-point inspection at various levels, from building these kind of printed circuit boards, then excising them after successful testing, and then going through various stages of manufacturing, boot loading, and so on and so on. And the second one is the miniaturization of this pill-sized module, which was a 12-layer PCB with 50-micron traces and spaces, lots of blind vias and things that you need to verify in stacks with hundreds of bond wires and make sure that everything works. And you can imagine the level of complexity to make that happen, as well as all of the interfaces and modules that need to be programmed. What I liked about this project is that it's manageable complexity by, you know, few dozen people who know what they're doing, but everything that engineering is about is here. It's, you know, circuits, power, communication, security, encryption, embedded code, application software. It was just beautiful, and just kind of getting everybody to learn. Just to get you into the hardware lab, beyond what typically hardware people do on many of these chips, we validate all of the chips in the systems context for, in this case, wireless power is shown, stimulation sensing, the control with all the embedded code. And once you demonstrate that feasibility, then you graduate that to the next level of maturity, which was not in our statement of work, but it had to be done, and we did it, to have external trial device, and then you finally get to the implant scale. Now, when you get to the implant scale, actually the most challenging part is verification. Now you have a tiny piece that you really have hard time probing and touching and needs to be thoroughly verified. Well, then we build these kinds of custom-based pogo pin sockets with sticking pins to be able to put it in a clamshell, put all the embedded code with developer version software for display of the recorded signals, as well as the oscilloscope view of the stimulation that is delivered. And you can see over here in vitro experiments, when you put a signal into the reference electrode, then you put a stimulation, then you need to pick up the reference signal as well as the stimulation and be able to clean the artifacts. And you can see here just the demonstration of this. At the developer version, you program the amplitude, and you have the switch matrix to program the drivers to various contacts. You can see the amplitude going up as you program it. Using this custom developed code, you can do the stimulation pulse width, and you're not limited by the square pulses. You can put custom waveform shapes as you like. And this is just one example showing random waveform shape that is charge balanced. And then you can see the response to that is programmed. And then building the whole system verification beyond that. I mean, when you think just about technology development, you rarely think about all of the verification collateral that you need to bring. So this was the motherboard for us to be able to validate components at various levels of maturity. Before packaging, after packaging, we have different connectors. As these components graduate to different level of maturity, we can just put them in this whole system context, whether that is emulation-based or the real hardware, together with the external device that is wired or wireless with all the graphical user interface to demonstrate all system components, full communication chain, control from PC application and graphical user interface. And so this was really interesting part of experience for us to really do it, to de-risk major elements of technology that, you know, need for sure another level of iteration, and I call, phase 1, phase 2 DARPA technologies are generation 1, generation 2 R&D. So what we need really is generation 3 level of maturity. But in order to get there, people ask about validation, and that's a fair question. So that's where we use this external device, which I call cracker stack, because it's really the size of a crackers, and we put colors that 5-year-olds can assemble these devices like Neuro Lego. So we have all of the active electronics from the implant scale, the human quality validated according to 14708-3. And we built this external device that we cleared through a clinical engineering group for human subject experiments at UCLA. And you can see what we really want to do with this is to collect real-world evidence of the functionality of these devices to inform the generation 3 and also establish a track record for downstream FDA submission. This is showing just the interface and device that is made in a package to interface with the adapters to the clinical arrays for neon codon. And here we are showing concordance sample of a channel showing the neon codon clinical equipment and our device practically, showing imperceptible differences in the time and frequency domain. We also record spikes. We have the fully automated procedure now to gather stimulation response maps on incoming patients to really kind of play a piano on the brain, because when you see so many different things that you can do with waveform shapes and so on, the real answer to that is automation. And you have to do that to really understand what happens in the brain. And there is a lot really to be done to bring this to reality, but I just want to kind of give you highlights and end by saying that it is unacceptable that in today's technology, where everything advances so rapidly for consumers, we are doing so little for medical devices. I like to say that we should stop implanting telephone poles in people in the era of smartphone technology. We really have a golden opportunity to merge modern brain-computer interfaces and big data analytics in a kind of medical device as a service, personalized medicine model, and bring modern technology to modern medicine. Be happy to take as many questions as you have. And just to acknowledge the UCLA clinical team and UCSF SUBNETS team and various people from these institutions who made it all happen. Thank you.
Time for some questions.
Hi, great presentation. For the human trials, clinical trial, is this like epilepsy patients that are undergoing epilepsy monitoring?
Yeah, so thanks for bringing that question. So like I said, that epilepsy monitoring is really the golden window of observation for pretty much all of the research that's going on in the clinic. All the results in mental health, memory, primary indication is epilepsy, and typically these patients have comorbidities. We also are looking into other indications that are primary indications, such as PTSD, chronic pain, Parkinson's disease, because what we really want to do is to OCD as well, to have indication agnostic validation of the technology that we claim to be platform. So at the end of the day, I'm looking into the anatomical placement of the electrode contacts and stimulation response maps that is agnostic to indication. But epilepsy monitoring is one of our main pipelines, and we do look into adult epilepsy as well as pediatric epilepsy.
More questions?
This is a very interesting talk. I was just wondering, have you ever tried to improve about the impedance mismatch, the contact issue of these deep brain stimulation electrodes?
The impedance mismatch of the electrodes themselves, correct? Yes, so that's a whole line of work that I didn't cover in detail that was done by our collaborators from Lawrence Livermore. We had extensive co-design of those electrical parameters that include all the variance in impedance over time, as well as the traces and how do we actually put together through the cable 64 channels where you can record and at the same time stimulate. So if you have, let's say, adjacent contact that you record from, and then you have a stimulation on the adjacent contact, which is plus minus 5 volt compliance, where you need to record from a few microvolts. So yeah, we looked into all of those issues, and we have a lot of data to show those longevity studies for the contact performance.
I have a question. So it's great work. Now, in terms of closing the loop, have you done experiments where the current state of the brain affects, right, your stimulation strategies and where, right? Have you validated the closed loop aspects of this?
Yeah, thank you for asking that question. I would like to give a really kind of gentle introduction to Miriam's talk. Miriam, you're going to talk about this, right? About the closing the loop. So Miriam was part of our team, and I appreciate you giving the opportunity to highlight her work. So she has developed algorithms to actually do the closed loop study that is based on several steps in which you do the system identification for a patient. And then she developed a nice theory in which she had a one metric tell-all, which was called integrated mood score, based on which you threshold the stimulator to be on or off. And this kind of one synthetic measure of the mood. But there is a lot more to it. And in fact, in this controller module, we have embedded Miriam's algorithms to be able to do responsive closed loop stimulation. We had a lot of human clinical data to inform the development of the algorithm, but we haven't reached the final point in which this very technology would be implanted in patients. There is a lot of things to consider there, including liabilities and approvals and enrollment and practical life issues. But yeah, we looked into those very carefully.
Very good. That makes some great linkages to the other session. Let's thank Jan again.
Thank you.